Remember that the character of a representation is the map that takes a permutation, well, if this is a representation of the symmetric group, it takes a permutation to the trace of its representing matrix. So one way to compute characters is to compute the representation and then take traces of the matrices. But there are also formulas for computing the traces directly from the element of the symmetric group instead of constructing the representation and taking the traces of the matrix. Let's let eta lambda be the trivial character induced from a Young subgroup of type lambda to the whole symmetric group. Now it turns out that if we want to apply eta lambda to a permutation W, that's equal to the number of ways to merge the cycles of W to form an ordered set partition of type lambda. An ordered set partition of 1 through n of type lambda. I guess it would have to be 1 through n because the elements of the cycles of W are letters 1 through n. Now, this is a class function because it's a character. So it's sufficient to do the evaluations for one permutation of each cycle type, because if there's two permutations that have the same cycle type, we're going to get the same answer. So let's write down a couple permutations and their cycle type. So we have the identity, which has cycle type 1, 1, 1, 1. And then if we want a permutation of cycle type 2, 1, 1, this is the 1, 2 cycle, so that's the 2, and then 3 and 4 form their own cycles. 2, 1, 4, 3 is a good permutation of cycle type 2, 2. 3, 1, 2, 4 is a good permutation of cycle type 3, 1, and 4, 1, 2, 3 is a good permutation of cycle type 4. So let's put eta 4, eta 3, 1, eta 2, 2, eta 2, 1, 1, and eta 1, 1, 1, 1 values in these columns. So for eta 4, we want to merge the cycles of W, so we'll pick a W. Oh, actually, you know what, this would be a lot of computation. I just want to do eta 2, 2, and then I'm going to let you guys do the other ones for homework. So we're going to merge the cycles of W to form an ordered set partition of type 2, 2. So for 1, 2, 3, 4, the cycles are all the singleton cycles. We want to merge those to form an ordered set partition of type 2, 2. So we could put 1 and 2 together in the first block, or 1 and 3 together in the first block, or 1 and 4 together in the first block. And then we could put 1, so here we've got 1 in the first block each time, we could put 1 in the second block. So we could just switch the order of these, switch the order of these, switch the order of these. So we've got 6 total ways to combine these to get ordered set partitions of type 2, 2. So that's 6. And then if we look at 2, 1, 3, 4, so 1 and 2 have to go in the same block now. So I guess those are the only ways to merge these cycles together to form a block of size 2 and a block of size 2, ordered. So that's 2. And then 2, 1, 4, 3 has cycle notation 1 and 2 together, 3 and 4 together. And I guess there's just 2 ways to do that also. And then 3, 1, 2, 4 has cycle notation 1, 3, 2, and 4. And there's no way to merge cycles together here to get cycles to get blocks of size 2, so that's 0. And similarly for 4, 1, 2, 3, which has cycle notation 1, 4, 3, 2, there's no way to merge cycles together here to get blocks of size 2, so that's 0. Alright, now let's observe one thing, and that is that eta lambda of w is a non-negative integer always. And our formula is that eta lambda of w equals cardinality of some set R. And if there's a number which is a non-negative integer, then I guess this is the nicest possible formula for it, the cardinality of a set. Because if we ever come across it in a proof, we can picture the set and maybe do something with the set rather than remembering what the actual integer is. So now let's look at induced sign characters. Let's let eta lambda be the sign character induced from the Young subgroup S lambda to the symmetric group Sn. It turns out that a formula for eta lambda of W is sine of W, which I'll write as -1 to the number of inversions in W. Times eta lambda of W, which we just computed. So let's put the sine of W, actually let's stick it in here because there's lots of room. So the sign of the identity matrix, the identity permutation is 1. The sign of generator 2, 1 is -1. The sign of S1, S3 is 1. This permutation has 1, 2 inversions, so that sign is 1. And this permutation has 1, 2, 3 inversions, so that sign is -1. So eta 2, 2 of W is 6, -2, +2, 0, 0. Now we'll observe that eta lambda of W is an integer, not necessarily non-negative. We get a negative sign here, and we could have gotten a negative sign here had the absolute value not been 0. And the formula is -1 to the cardinality of one set times the cardinality of another set. And if our formula is going to turn out to be an arbitrary integer, I guess that's the nicest formula we could possibly have. It couldn't be just the cardinality of a set, because that wouldn't tell us where the negative sign comes from. So we've got a sign part of the formula and an absolute value part of the formula. If we just wanted to know the sign, we could pay attention just to this set. If we just wanted to know the absolute value, we could pay attention to that set. All right, now irreducible characters are more characters that there are formulas for. Although I warn you, this is not a very nice formula. So the formula for irreducible characters, the best one that we know, is called the Murnaghan-Nakayama rule. Let's let chi lambda be the irreducible Sn character indexed by lambda. The Murnaghan-Nakayama rule says that if we want to evaluate chi lambda at W, this is the sum over a certain tableau T, -1 to the height of T, where the sum is over border strip tableau of shape lambda and content equal to the cycle type of W. So now I have to define what is a border strip tableau of shape lambda and content mu, and what is the height of a border strip tableau. So call a Young tableau, which is a filling of the Young diagram of shape lambda a border strip tableau of content mu. Let's say mu is mu1 through mu m, and that's a partition of n. If there are mu i's for I equals 1 to m, so that's what content mu means, and rows are weakly increasing, columns are weakly increasing. And border strip means, well, so all the occurrences of the letter I form a border strip. So that means that in French notation, something like this shape. And in English notation, something like that shape. And height of a border strip is its actual height minus 1, and height of the tableau equals sum of the border strip heights. So just picking out a border strip tableau, satisfying all the conditions and computing its height, that contributes either 1 or -1 to the formula. Now we have to do this for all border strip tableau of shape lambda and content cycle type of W. So let's do some examples. This is all important, but I suppose I have to erase some of it. So I think I will erase the definition of border strip tableau here. All right, let's make our list of permutations. So 1, 2, 3, 4 has cycle type 1, 1, 1, 1. 2, 1, 3, 4 has cycle type 2, 1, 1. 2, 1, 4, 3 has cycle type 2, 2. 3, 1, 2, 4 has cycle type 3, 1. And 4, 1, 2, 3 has cycle type 4. All right, so we want to actually, let's choose lambda equals 2. Sorry, 2, 2, like we did before. So we want to draw a border strip tableau of shape 2, 2, and the number of 1s, 2s, 3s, etc. in it is going to be determined by the cycle type of the permutation. All right, so if the cycle type is 1, 1, 1, 1, then we're going to have a single 1, a single 2, a single 3, and a single 4 in the tableau. Now they have to be arranged so that rows are weakly increasing and columns are weakly increasing. So I guess there's 2 ways to do that. And then each of these single letters is a border strip. Each of them has height 1 by normal human standards, but we're going to count them as 1 minus 1. So these heights are 0 plus 0 plus 0 plus 0, and 0 plus 0 plus 0 plus 0. Then the height of the tableau is going to be -1 to the sum which is 0, and negative 1 to the sum, which is 0. So we've got 1 plus 1. So our value of the irreducible character chi22 at the identity element is 2. Now let's look at 2, 1, 3, 4. This has cycle type 2, 1, 1. So we're going to put in 2 1s, a 2, and a 3. So we could put the 1s in the same column, and 2 and 3 there. Or the 1s in a row, and then 2 and 3 there. Now the heights, the normal heights of these border strips are 2, 1, and 1, but we're going to count them as 1, 0, and 0. So we've got negative 1 to the 1 plus 0 plus 0, which is negative 1, and negative 1 to the 0 plus 0 plus 0. Then we add together our contributions of negative 1 and 1, and we get 0. So that character valuation is 0. Now let's look at permutations of type 2, 2, with our representative being 2, 1, 4, 3 here. So that means we're going to have 2 1s and 2 2s. And I guess for this rule it doesn't even matter. Well, for computing it, we're just looking at the cycles really. We're sort of forgetting about the permutation. But what we're computing is chi22 of this permutation, chi22 of that permutation, etc. So we want 2 1s and 2 2s. So putting those in border strips, we either have the 1s and 2s in a column together or in a row together. That's the only way we can do it, so that rows and columns increase weakly. So here we've got a contribution of negative 1 to the height 1 plus height 1, which is 1 less than what we see here, 2 and 2. And then here we've got negative 1 to the 0 plus 0. In both cases we get 1, so the contribution is 2. And now for 3, 1, we can put the 1s in a border strip like this, or in a border strip like that. I'm thinking of these as French tableaux, so we're increasing that way. So these are the only two border strip tableaux of content 3, 1. So this contribution is negative 1 to the height is going to be 1 plus 0. And again, this height is 1 plus 0. So negative 1 plus negative 1 is negative 2. And then for cycle type 4, we want to put 4 1s in there. But a border strip can't have any 2 by 2 subshape in it. Border strip has to be something like that. It can't have a, we can't fill this 2 by 2 Young diagram with 4 1s which form a border strip. It wouldn't be a border strip. So we're going to get 0 here. And let's just observe one thing about this formula, which I am not clear about, is that what it does is it gives us something like negative 1 plus negative 1 plus 1 plus negative 1, whatever. It's a sum of a bunch of 1s and negative 1s. So the sign, whether it's positive or negative, of the answer is not clear until we add all of these 1s and negative 1s. You can't see ahead of time whether you're going to get more positive ones or more negative ones. And then the absolute value of the result is not clear until the end. If this were a nice formula, now it's positive sometimes and negative other times, it would be -1 to the cardinality of one set times the cardinality of another set. So we could see the sign and we could see the absolute value. But nobody knows a formula of that form for the irreducible characters. So we're stuck with this sum of a bunch of ones and negative ones. That seems to me would probably be hard to use in a proof because we just don't have a mental picture to put along with it. The end.